Hi everyone. I hope you can hear me. If not, maybe say something now. Okay, yeah, so thank you very much to the organizers, first of all, for putting together this amazing workshop and for inviting me to speak. I'm very excited to be here today and tell you a bit about the history of NetHack and how it was proposed as a grand challenge for AI and now a grand challenge for RL and LLM agents alike. Nope. See? Okay. So I want to start this by asking a question to all of you here. And the question is like, what are the grand AI challenges in 2025? Very curious to hear. You can mention any benchmarks you consider grand AI challenges, or any capability or new task you'd want to see posed as a grand challenge. Any ideas?
Is this a question of what we want to see in future, or what are the examples that we have now?
Yeah, it can be anything. Yeah, what would you consider a grand AI challenge today?
Long horizon tasks.
Okay, yeah.
Physical intelligence, understanding the physical of the world.
Yeah, great answers.
Just folding laundry.
Oh yeah, yes, please. Very great answers. Yeah. Anything else? Oh, okay, a lot of like robotics, physical intelligence, embodied AI.
Like the challenge with RKGI.
Yeah, yeah, these are all
Very
great.
long-lived agents.
Long-lived agents. Okay, yeah, yeah. I would love to see a benchmark on that. Okay, anything else?
Out of distribution, generalization?
Yeah, yeah, great answers. Yeah, yeah.
Learning?
Yeah, definitely all great answers. I think maybe, okay, the specific, pointing to specific benchmarks would help here, right? Something that exists and we can try out our best models on. Yeah, that's a good one. Okay, I'm gonna maybe like just add a bit more flavor to these, right? And change the question to a grand AI challenge that will still be a challenge in 2030. Anyone wants to change their answer from before? Okay, so we're still confident we won't solve RKGI and what was the other one? Maybe like folding laundry in 5 years. That's good.
It'll last us to be solved.
Yeah, it would be nice if it were sooner.
I think the ethical aspects of AI will still be forever a challenge.
Yeah, for sure. Yeah. Okay, last call for an answer to this question.
Open-endedness?
Yeah, what's the benchmark though?
Yeah. I mean, you're going to present it though.
Oh, yeah, okay. Okay, let's move on then. Okay, so that's, a bit of the, let's say, the introduction to this talk and a bit of the questions we're trying to pose here. So of course, this is a question that has been asked in the community and people give all sorts of answers, right? Perhaps a few years ago, people might have said that getting a gold medal at IMO would be super impressive and won't be solved for many years to come. But today we do have models that can do that. And then, you have answers from Jim Fan, who would also really love an AI to cook a nice dinner, right? So very focused on embodied AI and physical intelligence. And then Tim Rocktaschel, who's, of course, the proposer of NetHack and really like, he advocated for this for a really long time as a challenge for AI. His answer is that assuming it's a general purpose learning agents, let it read the NetHack wiki and try to ascend on the NetHack game. So basically, just try to solve the NetHack game with the same sort of like experience or knowledge as a human might have. And then he adds, probably this is more of an ASI benchmark. NetHack is notoriously difficult for humans as well. And there's definitely a world we can imagine that these agents can become superhuman on the game of NetHack. So let's see, taking NetHack as a test for AGI, let's now look at the current benchmarks we use to measure performance of models, right? And if you've been following the broad AI field, you might have noticed that these benchmarks are saturating very, very quickly, right? So you can see on this plot here, just like how much we've made progress on them from in less than a year, right? So from September 2023 to May 2024, some of these benchmarks really had quite low performance. If we look at GSMAK, this math reasoning benchmark, you'd see performance was was less than 20% or so, and now it's close to human levels. Like pretty much all of these are saturated. In fact, including some of these ARC or ARC-AGI benchmarks. And there's even a website called Killed by LLM that collects this set of tasks, right, that get saturated by models. And every year you see more and more tasks on this list. So what's going on, right? And the question is like, how can we come up with some challenges that stand the test of time and can remain, like things that we can continue to make progress on for slightly longer than perhaps a year. And in contrast, if you look at the performance of our best LLMs today on the game of NetHack, you observe that it's pretty much, it's very, very low, right? And it hasn't progressed that much in the past few years, despite a lot of progress with the LLM. So we see, for many of the models, it's flat out 0, but maybe now with some of the best models, in this case, this Grok 4 model gets to 1.8%. Still seems very, very low. And if you compare to other types of even like games or these kinds of interactive worlds like Baby AI, Crafter, and so on, you still see that there has been much more progress on these types of tasks relative to NetHack. So like what's going on in here? So let's see a bit what makes NetHack a good AI grand challenge. So this is a game that is extremely complex for humans as well. So the game is that you need to, you're in this roguelike dungeon, and you need to go down many, many levels, retrieve what's called the Yonder Amulet, and come back up through all of these levels and survive, lots of different monsters that are trying to kill you, and be able to collect lots of resources and use them, manage all of your resources, and know how to deal with all sorts of different entities so you can make progress on these. So this is procedurally generated. Every time you play the game, you get to be in a new dungeon, right, that has a completely different layout, and perhaps like with somewhat different like properties of the entities and so on. So every time you're basically in a new state. So you need to really, in order to do anything on this game, you need to be able to generalize, right, and have a pretty good state representation so you know how to act in every state that you get to see. It's also partially observable, which is important, a bit closer to many real-world scenarios, right, where we need to deal with just being able to observe part of the world and not having access to the rest, or being able to reason from that partial information. As I mentioned, has very rich entities and dynamics. So there are all sorts of things you need to learn so in order to be productive in this environment. It's very, very long horizon. It probably takes humans like tens of thousands, if not like hundreds of thousands, to play different versions of steps to play different versions and succeed in this game. And it's an extremely hard exploration problem. You get some signal from the game, such as a score, right, or how much health you have or other things, but it's not always very well correlated with what you need to do, right? So you need to somehow be able to reason beyond that single number and get like learn from richer forms of feedback in order to make progress. So you can see here an example of the observation of this game. You have what's called this like sort of like a message you get from the game that somewhat describes the state you're in, but not fully. It usually focuses on a particular thing that happened in this observation. You get to see this partially observed part of the world, right, with the agent and what's happening around it. And you also get some metrics, like some health stats or how many steps you've taken so far. So yeah, this was proposed in 2020, as you can see here, so about 5 years ago. And the reason this was proposed was to create this RL environment that's sufficiently complex, but still fast to run. So at the time, there are like lots of like very complex 3D worlds or Minecrafts, very interesting RL environments, but they're quite slow, right? Because they had like this strong visual component. So it was hard to do a lot of steps on them. And then you had certain games that were a bit simpler, but not just like they were fast to run, but perhaps not as challenging. So we wanted something that had both of these components. Yeah, so we proposed NetHack because we thought this would be like sufficiently complex to drive long-term research on problems such as exploration, planning, skill acquisition, and language conditioned RL. And I would say this still remains true to until today, right? So many of these problems haven't been solved, and it's like there's still NetHack acts as a way to try and probe these kinds of skills. And finally, we wanted to test robustness and systematic generalization of RL agents because you need to really generalize in order to do anything at all, because you never get to see the same state twice in this game. We also had this NetHack challenge at NeurIPS in 2021. So we proposed this for the community as a competition, and we got lots of different submissions, very creative types of agents. And what I want to highlight here is that, interestingly, the symbolic agents perform much better at the time than the deep learning ones. So that's quite interesting to see. And here I have a video of one of these, the winner of that challenge at the time. So you can see a bit how the game looks like and what the agent is trying to do. It's a bit hard to parse if you're not familiar with the game, but you can see that it sort of like navigates and tries to interact with various things to make some progress. And this is all symbolic, so it doesn't have any kind of neural network component to it. So what are the specific challenges that NetHack poses for RL agents? In particular, I would say these are the problem of long horizon planning, right? So the RL agents haven't been historically particularly good at decomposing tasks into low-level skills and being able to learn both the high-level policy and low-level skills at the same time. And of course, it's, again, very hard exploration problem. So it's just very hard for the agent to make progress, right? Because there's so much it can potentially do, right? But there's not very clear signal on what's good and what's not so good. And more recently, this has been converted into an LLM benchmark. So this is called Balrog and has a collection of tasks, so NetHack and a few other ones like CraftTags and so on. So Davide Paglieri has been leading this work and just making it very easy to test any LLM on this, right? So it's just the LLM takes as input the observation it gets from the game and then outputs an action, and then we get to evaluate, and we have this nice leaderboard where you can see how they stand. This is progress on their entire benchmark, so it's not representative on NetHack. As I showed on NetHack, it's much lower, around from 0 to 2% or so. So you can see that, for example, on NetHack, even the very best Grok 4 model, dies basically on level 1 of this game. So it doesn't make a lot of progress, and it's killed by a house cat, sadly. Yeah. So here we have the results from this Balrog paper. So you can see again, if you compare to all these LLMs, right, on all these different tasks like Baby I, Crafter, and so on, they can at least make some progress. More on some than on others, but the NetHack, it's basically close to 0, so not doing anything that meaningful. And the challenges for LLM agents, right, is they really struggle with this fine-grained control. So they really struggle to go from observation to the low-level action, right? And they also don't really update, right? They don't update their weights in all of these, right? So it's all just kind of generalization, right? Maybe updating a bit using their in-context learning, but you don't really get to update the policy from feedback and improve it over time, which is another disadvantage for these types of games. So how can we bridge this gap and try to connect a bit the best of both worlds, right? So connecting the advantages that LLMs have with the ones that we get from training with reinforcement learning. And the idea here would be that maybe, we can try to use the LLMs to generate these high-level plans that they seem to be great at. We've seen such examples in perhaps robotics and other situations, and also use RL for the thing we know they're also really good at, which is training, some specific policy to do something if we have a good enough way to reward them for that. So that's one of the core ideas of this recent paper called Maestro Motive. So this is a new approach from Martin Klisarov and others. And you can see here that, sorry, I'm not sure how to move this. But you can, the core idea is that we can use the LLMs for high-level planning and do low-level control with reinforcement learning. And how do we do this more specifically? So what we want to do first is to figure out what are the skills that would be helpful to make progress on this game of NetHack. So in this case, we ask, we use our own human intuition and knowledge about the game to come up with a small number of skills. So these will act as the sort of like sub-agents or sub-policies for the high-level planner. So you can imagine, perhaps you might want a gold collector, right? Just like some agent that can go ahead and collect resources that you need, and is very specialized and does that very well. You might need a descender, right, that is very adept at navigating through this space, right, and like going down these different levels. You might need a monster slayer to fight off monsters when you encounter them, and all these kinds of things. So this is done, again, through our own human knowledge. But I would say in the future, I can definitely imagine this also being done by an LLM, and essentially just asking for perhaps like conditioning on NetHack's wiki or other knowledge about NetHack to come up with these kinds of skills. I don't think that would be too challenging for them at this point. And then we are going to use the LLMs as proxies of human priors. So we use them in two particular places. First, to provide feedback to learn these low-level skills. And second, to do the high-level planning, right? So be able to take the sort of like hard NetHack task and decompose it into low-level skills and make progress on those. So more specifically, the way this will work is in 3 different steps. So first, we're going to craft these skill-based, so these are skill-specific reward functions, and we're going to train this with AI feedback. So then we're going to end up with, just like reward functions for each of the skills I mentioned before. In the second step, we're going to use the LLM to come up with these kinds of high-level plans. So this will operate in the space of the skill. So it will just figure out, like, for a given state, what skill should be using and how to change perhaps from one skill to another. And we can refine this through in-context learning. And finally, we're going to teach the low-level skills through reinforcement learning using the reward models we trained before. So here's an example of the kinds of tasks we look at in this paper in Maestro Motive. So these are not the full NetHack tasks. It's sort of like very much inspired by NetHack, and it operates directly in the NetHack environment. But the idea is to simplify, right, and just come up with a task that is very descriptive in terms of what the agent needs to do. So perhaps he needs to collect, I don't know how many items, and like go down 2 levels and survive for a number of steps. And you can see here a demo of how the method works. So you take this. You have this policy over these different sub-agents or skills, and that decides which agent to use in each state. And then you kind of like change from each of these different like skills or sub-agents until you manage to complete the task. So that's how it works at test time. And we have a number of these different tasks, and we train on some. We use some for training, and some that are completely not seen at test time. So at test time, importantly, we don't do any learning or any training on those tasks. It's all zero-shot generalization. So the high-level policy will simply learn how to combine the low-level skills and be able to operate and solve or make some progress on those tasks. OK, so for the first training step, again, we're going to have our large language model in here. We're going to prompt it to elicit preferences for each skill. So we provide it with 2 observations, and then we ask which one is better for a particular skill. And then we end up with skill-specific reward models. So here's, like basically we construct this data set with various observations from the game of NetHack in this case, and then we train this type of reward model. And again, like we have one reward model for each skill, because you can imagine, certain actions are more useful for certain skills than other, right? If you have a kind of like a gold collector, then you want to collect gold, not necessarily move down the dungeon levels and the other way around. And here you can see an example of this prompt, right? So we explain to the LLM how it should try to compare these 2 states, and we provide it with representations or like description of each of the states. And in particular, it's sort of like focused on the difference between what happened in the last action that the agent took. So now you're going to have your LLM that takes as input the task specification and skill description. So you give it all the skills that you have in your archive and the task that you're trying to solve, and you're going to ask it for a piece of code that will be your high-level policy, right? So this will essentially tell you just like for each state what type of agent to use. So here's, you can see the example for a prompt for this LLM. And we also ask it to come up with some unit tests. So it sort of like simulates the environment itself at this high level of abstraction. And then you can use that to refine the model a bit. So you ask it to generate this high-level plan and some unit tests to check if the plan is good or not. And then you're going to do a few refining steps using this over here. So in practice, we do 3 repetitions of code refinement using the self-generated unit test, and that improves the code, the high-level plan that it comes up with in some situations. So here you can see an example of the code that the LLM generates. So this will be the high-level planner. So you can see here, a function for selecting a particular skill. And you see, okay, if some condition is met, then you're going to use a particular agent. If something else happens, use another agent, right? So it's quite complex in this way, and just like a very long list of if-else statements. And the LLM is able to come up with this through just like having some knowledge of NetHack and some kind of like common sense on what to do in each of these scenarios for this particular game. And finally, we want to train the skill policies. So the way we're going to do this is by trying to train a neural network for all of these policies. So here what we have is that, again, we're going to use our high-level planner, which we already have. And this one will take as input the state of the game. So that's like the actual NetHack state. And then it will output a skill index, right? So just like what is the particular skill that should be used for the state. And then we're going to train this kind of like skill policy, right? Skill neural network that will take as input the state from the game, as well as the skill index, right? So what skill it should try to follow. And it will output an action that then gets executed in the game. And we train this with RL using the skill-specific rewards we learned in the first phase. So yeah, the important thing to know here is that this is we can use a single neural network that adapts to this behavior, to these different skills, which is quite neat. And this is also quite nice because it already operates in a way in a sort of like a way in the own policiness of the high-level plan. So yeah, these are the main components from the algorithm. So again, the LLM's high-level plan and RL-trained skill neural network. And now what do we do at test time? Well, at test time, we get a new task specification, right? So like a complete new task the agent hasn't seen, and it does this zero shot, right? So you just generate a high-level plan with the LLM in this code format, and then that you know how to execute those because you've already trained the skills and they work reasonably well, so you can compose them to solve these different tasks. So there are no additional gradients, and it's all done through this idea of skill recomposition. And here are some of the results on this task. So as I mentioned, these are just some NetHack-inspired tasks from the early game of NetHack. So they're still pretty early on, but still very, very challenging. And we can see that the performance of our approach, Maestro Motive, improved significantly on the other baselines, right? So if you take just the LLM policy and try to run it zero shot on these new tasks, you get pretty much like 0% performance. With Maestro Motive, you can get, you can either make like a bit of progress, some like 1% or so, and in some cases, you can get like pretty significant improvements, like up to 46% success rate on on some of the tasks in here. You can also compare it with some methods that do task-specific training, but again, these are methods that are trained directly on the task that is used here. And Maestro Motive does this completely zero shot at test time. So in the case of task-specific training, you can use something like the precursor to Maestro Motive, which is just motive, and in this case, we don't have any of the hierarchical components. So the idea here is that we simply use the AI feedback part. So we train like a single policy to learn from AI feedback, and that gives us a bit of improvement on some of these tasks relative to just using the in-game score. And then you can also imagine other ways of having some intrinsic motivation for the agent, so we can try to make some progress on this task, which is using some kind of embedding similarity between the state or trajectory of the agent and the final, the task description, like the kind of ideal state you want that to be in. So yeah, the TLDR is that the Maestro motive is able to generalize zero-shot to a variety of such complex tasks on the game of NetHack. And you can see here some more comparisons with other types of agents, like hierarchical behavioral cloning combined with PPO and so on. Again, you just don't see these methods doing anything meaningful on these types of tasks, whereas at least Maestro motive can do something on these. So yeah, I just want to, I guess, yeah, like remind the purpose of this talk, right, which was that NetHack really has been in a way, a grand AI challenge since 2020 for the past 5 years, which is not something we can claim about many of the other benchmarks people have been proposing. And there's still a lot of room for improvement, right, for both RL and LLM agents, and perhaps combining them. Combining the strengths of each might allow us to make a bit more progress. So I'd love to see more progress on NetHack in the near future. Yeah, with this, yeah, I'll conclude my talk, and also thank you to all the amazing collaborators who contributed to this work. I couldn't list all of them here, but just wanted to give a special shout out to Tim Rocktaschel and Heiner Kuttler, who have been proposing this and kind of like created and advocated for NetHack 5 years or so ago, and then Martin and Pierluca, who have been leading the Maestro motive and motive works. Thank you, and I'd be very happy to take any questions.
Yeah. So for the training, I'm still confused. You said that you're showing examples of skills, and you are telling the LLM to judge which one of them is a better execution of that skill. But still, when you said when you come to the deployment, you are giving a task description and you want to get the plan. So I don't see where is the bridge here of getting a task description and getting a plan. This is not the same as I'm showing skills and you judge whether this is good and this is better than this. So maybe if you could put more details there. The other point is during inference time, even if it generates the plan in Briar and give you the Python code to judge it, during the execution, something could went wrong due to dynamics in the environment. Then the LLM has to re-engage again and maybe update the plan according to the current situation. Also, how do you handle these situations? Thank you.
Yeah, great questions. Yeah, so so the LLM is the one that operates from the task description to creating the high-level plan, and then you go from then the plan decides what skill to use, and then that skill gives you the action that you execute in the environment. So I hope maybe that clarifies a bit the first question. And on the second point, we don't update so we don't do any updates in any way at test time. I think that's a great direction for future work, trying to have more feedback to update a high-level planner, of course, or perhaps like even the low-level skills. You can also imagine, like trying to generate the skills as you learn, right? Or perhaps like add more skills over time. So all of these are, I think, great future works.
A question about the benchmark overall, which is, what are your hopes for it? So is the hope to get to better algorithms? Is it to get to just better performance by any means possible? Like, there's differences when you're sort of starting from scratch or starting with an LLM. What are your hopes for the NetHack benchmark?
Yeah, that's a really great question. Yeah, I would say I think it can still be very helpful to make progress on some of these like big research questions, right? So ideally, we would want to see I think in my ideal scenario, just like see someone be able to learn how to play NetHack at human level, let's say, right? Given like somewhat similar, like information in terms of like having access to the wiki or other types of information, and then like being able to learn, let's say, as quickly or perhaps like more quickly than human on NetHack. And I think there's still many open questions, right, that it tries to target, like just like research questions, right, in AI more broadly, right, of like exploration, long-term planning that we haven't fully cracked, right? So I think this, just like the fact that we have these amazing LLMs, but they cannot do much in NetHack tells me there's something, there's like a gap that needs to be breached.
Yeah, thank you very much.
Yeah.
Last question. But I was going to say we need to move on to the next.
Yeah, I was just going to ask. So yeah, I think trying to pull in the language in lots of ways is really useful because games generally have language that tell the player what they should be doing. The wonder I have, and maybe you have insight on this, is like how much language when we do LLMs now in this, does it actually need? Like, does it need like a whole wiki? Because at least when we're building the games, that doesn't exist. Usually the community like builds that up over time. So where are we in terms of how little language we can get away with and get things working well?
Yeah, that's an interesting question. Yeah, to be clear, right now we're not feeding directly the wiki into it. I think there's an assumption, right, that it's probably seen it, right, and can extract some of those things. Yeah, I think it would definitely be interesting to also see a version of this that can work without the wiki, let's say. Yeah. Right now, it definitely helps a lot, right, to have this language component and have these like priors on what are good like skills to learn on NetHack and so on. So I think it's extreme, like even way harder to do anything without the language component at the moment, right?
Yeah, great,
Yeah.
thanks.